You know, from the chatbots you talk to every day to the tools that translate languages in real time, almost all of modern AI is powered by one single core idea, the transformer. So today, we're going to trace the incredible evolution of this groundbreaking architecture. All right, here's the plan. We're going to start with that original 2017 blueprint that pretty much changed everything. Then we'll dive into how engineers tackled its biggest problems, like how to understand word order and how to manage these massive computational costs. And finally, we'll see how all of that led to the specialized models we use today. Okay, so let's set the scene. Our story begins back in 2017 with this one groundbreaking paper called Attention is All You Need. And really, it just completely revolutionized how machines handle language. Now, the core superpower here is something called self-attention. Okay, imagine this. You're in a library. To find the right book, you have a query, that's what you're looking for. You compare that query to the keys on the spines of all the other books to find the best match. And once you find it, you pull out the book itself, which is the value. Well, self-attention lets every single word do this at the same time, asking every other word, hey, are you relevant to me? This is how it figures out that in a sentence like, the robot picked up the ball because it was heavy, the word it refers to the ball, not the robot. It's brilliant. So this original design, it was purpose-built for one specific job, machine translation. It had an encoder stack to, read and understand the English sentence, and then a decoder stack to write the corresponding French one. Simple as that. But there was a really fundamental problem. In its purest form, self-attention just doesn't care about word order at all. To the model, a sentence is just a jumbled up bag of words. So how in the world do you teach a machine that dog bites man is a very, very different story from man bites dog? I mean, the model has to have a way to understand the sequence, right? Well, the first attempts were clever, but kind of flawed. One idea was to have the model actually learn a unique tag for first word, second word, and so on. But the problem was, this just completely broke down if it saw a sentence that was longer than anything it had seen in its training data. Another approach used a fixed mathematical formula, like sine and cosine waves, to encode the position. This worked for any length, which was great, but it was just too rigid. It couldn't adapt. But today, the most elegant solution is something called Rotary Position Embeddings, or RoPE. And instead of just kind of tacking on the position information, RoPE actually weaves it directly into the very fabric of the attention calculation itself. So here's how it works, and this is pretty cool. Imagine each word is represented by an arrow pointing in a certain direction. RoPE takes that arrow and just rotates it by an angle that's determined by its position in the sentence. So the first word gets a small rotation, the second word gets a bigger one, and so on. Now, the relationship between any two words is just encoded in the difference between their angles. It's an incredibly slick way to give the model a real sense of relative position. Okay, so with the position problem solved, a brand new hurdle popped up: scale. As researchers tried to feed transformers longer and longer texts, we're not talking sentences anymore. We're talking entire books. The original design just became incredibly inefficient and super expensive to run. And the issue here is something called quadratic complexity. Now, in simple terms, what that means is, if you double the length of your text, the number of calculations needed for that self-attention doesn't just double, it quadruples. And as you can imagine, that just explodes, becoming computationally impossible for really long documents. So to handle these longer texts, one really popular solution is what's called sliding window attention. Instead of every word looking at every single other word in the whole document, it only pays attention to a fixed number of its immediate neighbors. This just dramatically cuts down on the number of calculations you need to do. Another really clever innovation helped speed up the process of generating new text. Think of the original model like a workshop, where every single worker has their own complete, separate set of tools. It's a lot of overhead. But with grouped query attention, groups of workers now get to share some of the most common tools. And this saves a huge amount of memory and just makes the whole assembly line run so much faster. And even these seemingly small architectural tweaks have had a massive impact. Originally, the model would do a really complex calculation and then normalize the result to keep things stable. Well, modern models completely flip this. They normalize the data before the calculation, and they use a simpler, faster formula called RMS Norm. This one change made training way more stable and a whole lot faster. So all of these pressures, the need for a sense of position, the need for efficiency, and the need for different kinds of tasks, it all led to a split. The original one-size-fits-all architecture kind of fractured and evolved into three very specialized families. And this specialization is really what created these three distinct families. So you've got the original encoder-decoder, which is still perfect for tasks like translation or summarization. Then you have encoder-only models like BERT, which are designed purely to understand and analyze text. Think sentiment analysis. And of course, there are the famous decoder-only models, like the whole GPT family, which are absolute masters of generating new, creative text. So, in just a handful of years, we've watched the transformer adapt and evolve at this incredible pace, becoming leaner, smarter, and way more specialized. And I think it's just crucial to see that this evolution wasn't random at all. It was a direct response to fundamental problems: the problem of order, the problem of scale, and the problem of task specialization. Each one of these breakthroughs was an answer to a critical engineering challenge. But this journey of innovation is, of course, far from over. We've managed to make these models faster, we've made them more aware of position, and we've made them more specialized. Which really just leaves us with a final thought to consider. What's the next fundamental limitation that the next